All right, folks, it's about time. Let's get rolling. Welcome to the class again. Today's lecture 5, and we're going to learn about logic gates. I mentioned in the very first lecture that I'm going to keep on bringing this slide, from time to time. And one of the reasons is just, help us just follow along why we are doing what we are doing for today's lecture, and what we did yesterday or in the previous lecture, how you can connect the previous lecture with today's lecture, things like that. It's going to be really helpful when we go into our future lectures. But today we are going to learn about transistors, how they are built from semiconductors, and then from using those transistors we can actually create the basic gates, which are NAND gate, OR gate, and the inverter. And I'm going to start today's lecture with the transistor as a switch. And my question is, what is a semiconductor? So semiconductor is a magic material which has the property of that of both of the conductor and insulator. Depending upon the external parameters such as voltage, temperature, the semiconductor can act as a conductor and also as an insulator. And we'll see that over here. So you have a piece of a semiconductor which is positively charged. This represents the positive region of semiconductor materials. The two yellow regions that you see are the negatively charged areas on a piece of a semiconductors. And there's no current that is going to flow between these two yellow regions unless there is a conductive channel. This conductive channel is actually opened up when you place a piece of a material, which is usually a metal, encased in a piece of a glass in an insulator. So glass is being used as an insulator, and this gray rectangle box is basically a metal, and you place that material on top of those yellow region. When this we refer this as a gate, and when this gate is energized, or in other words an external voltage is applied, it creates a conducting channel allowing the electrons to move from this yellow region to the other region. In order to open up this conductive channel, we basically need source and drain. So this in the middle is your gate, this is your source, and this is drain. You can think of source and drain as input and output. So this is your input and this is your output. Once the source, when you apply an external voltage to the source, it will not travel from this yellow region to this yellow region unless the gate is energized. Okay? However, once you have the input energized and you also have the gate energized, this opens up that semiconducting channel again, which allowing the electrons to flow from source through gate to drain. And this way it completes the circuit and it creates the logic 0 and 1. So this is how it is working as a switch. This is a very neat device, also referred to as a solid state physics, because it doesn't have any moving parts. Like Hunter said, it can, if you look at diodes are also made up of semiconductors, usually silicon, germanium, or different other semiconductor materials, which are compounds of phosphorus, gallium, and indium. These are the hot semiconductor materials which are used for these applications. If you place these transistors, these devices, right next to each other, there's a way for us that we can actually create logic gates. So, for example, you have two of the transistors arranged in parallel, and to the gate I connect two switches, and both switches currently are set to 0 positions. Okay, you have the input of both the devices energized, and the output wire, if I place the output wires and connect them to a light bulb, I can create an OR gate right here, right? So notice this switch is 0, that means the gate is not energized, the electrons are not going to flow to the drain. But here the switch is 1, the input is energized, the gate is also energized, allowing the electrons to flow from the source to the drain, and that the output is connected to the light bulb. It's actually going to light up the bulb. So for all logic, any of the input is high, it's actually going to create the high at the output. And this is how we create OR gates using the transistors. If I change the wires such that the output of the one device goes into the input of the another device, right, which is right next to it, and then the output of that device is connected to the light bulb. This way I'm able to create AND logic, which means in order for the output to be high, both inputs need to be high. So notice here switch is 0 and switch is 1 here. So what is going to be the output over here? No electrons flowing. There's nothing going into the input of that transistor. So therefore, even though the switch is 1, the gate is energized, but there's nothing over here at the input, so nothing goes out of it, and the light bulb is not lighting up. However, if I change the logic where I energize both the gates by turning the switches to the on position, now the output here is 1 that goes into the input of the next device, and the output is connected to the light bulb, which lights up because both the logics are set to high. So this is how from semiconductor you make these devices, which are transistors, and then these transistors can be placed together in order to make basic AND gates or OR gates and inverters and whatnot. So today we don't have any supporting material. It's just me running the show, and you guys just sit and enjoy. So a logic gate is a digital circuit that performs a logical operation, either allowing a signal to pass through it or stop it. There are 3 basic logic gates, and those are AND gate, OR gate, and NOT gate. The inputs are to the left. We also refer them as wires, and the output is onto the right. This bubble sign, this small spherical thing is referred to as a bubble, which is usually right next to this triangle. We call it a NOT gate. An inverter. More about logic gates. To implement a logic gate in hardware, you use transistors. And by the way, there are 2 types of transistors. One is the BJTs. Those are known as the bipolar junction transistors. And another one is the CMOS, also referred to as a complementary metal oxide semiconductors. I'll explain what is the difference between the 2 in my future slide. Transistors are all encased in IC, an integrated chip. So if you have opened up your computer and you see something like this is what we referred as ICs, and inside this IC there are thousands and millions of transistors and other passive components, including capacitors and resistors, are embedded. And I actually have one slide that will blow you away how many transistors are inside that small IC. The Intel Pentium 4 processor has 55 million transistors inside. The A12 Bionic chip in iPhone X contains 6.9 billion transistors. We have come down to a level of nanometers. Like the smallest size transistor available is 5 nanometers, and Intel is trying to cut it down to maybe a couple of nanometers now, which is the biggest challenge. They have a facility in Arizona where they do that. Believe it or not, a few years ago, this was close to Waltham. I can't remember the name of the city, but that's where it was. But they moved to Arizona a few years ago. All right. It's 6.9 billion transistors and uses 40% less power than A11 Bionic chip. If you happen to have an iPhone 7, which I have, it has 3.3 billion transistors inside. So within a span of like almost 3 years, they have been able to double the density of the transistors in their chips. So fortunately or unfortunately, you might not see that things like this in the lab. We don't do it anymore, but the first lab is actually the simulation. So kind of give you like a hands-on working on how to deal with these chips. And they come in different packaging these days. So this is what we refer as a dual inline package. This is a 14-pin chip. If you look at this notch, usually this is pin 1, this is pin 7, 8, and this is pin number 14. We also have these surface mount ICs, which are like smaller in size. They're compact, they're flatbed. They allow just good, they just appear good and very small in size. One of the reasons the things are getting smaller, skinnier, and slim, that's because of this type of packaging. And it reduces the mounting area by almost 47%. So that's huge. If you see the inside schematics of the logic gates, which are inside these chips, they look something like this. So 7408, which is an AND gate, it has 4 AND gates, 4 2-input AND gates. Pin number 1 and pin number 2 are the inputs, and pin number 3 is the output for gate 1, and gate 2, 3, and 4. For the most ICs, pin number 7 is going to be ground, and pin number 14 is going to be VCC. And similarly, you have the OR gate and the inverter. The ICs are classified, there are different levels of integration. Right now we are at the very bottom, ULSI, which is ultra large scale integration. We're talking about millions and millions of transistors. So those of you who have already bought the Basis 3 board, right in the middle of the board you'll see a chip that has XC735A CPG236. That's the heart or the brain of your Basis 3 board. It's got millions, I think it's got over 5 million transistors and 32,000 logic cells inside. And this is just a normal below standard FPGA. Those which are very expensive, like I'm talking about $5,000, those have like a billion transistors in. So small scale integration, so these ICs can be classified as these. SSI usually have 3 to 30 gates per chip. So in my previous slide, you saw that N gate, which had 4 gates inside one chip. So that is considered a small scale integration class. If you move to the next class, which is medium scale integration, that have 30 to 300 gates per chip. Large scale integration have 300 to 3,000 gates per chip. When I was in the college, I was doing my engineering. This was a huge thing, VLSI. Very large scale integration, so we were roughly talking about 3,000 gates per chips. And then super large scale integration, 10 to 100,000 transistors. Those were used in calculators still today. And then the ultra large scale integration, we're talking about 1 million transistors. So we have entered an era of FPGA, field programmable gate arrays. This is the chip that I was talking about. It's from Arctic 7. It's made by this Digiland company. So we're going to move on to the logic levels now. And we know in a binary we only have 2 levels, either 0 and 1. 0 could correspond to 0 volt and 1 could correspond to 5 volt. And similarly, we could refer to it as yes or no or true or false. In a binary logic, the 2 levels are logical high and logical low, which generally corresponds to a binary 1 and 0 respectively. The 2 logical states are usually represented by 2 different voltages. Sometimes they can also be referred at 2 different currents as well. Okay. Moving on to the next slide. Logic family. The 2 most popular families for ICs are CMOS and TTL. And again, CMOS is the complementary metal oxide semiconductor, FET. So the earlier animation that you see was that of the FET. And then TTL, transistor logic, is BJTs, which is bipolar junction transistor. I believe when you take ECE 2201 microelectronics, you will learn more about these. FETs in the last decade or so have taken over and put BJTs in the background. And one of the reasons for that is FETs, they have a faster switching. They are less prone to noise. The density is very nice, meaning you can have a lot more gates in a small piece of silicon versus compared to the TTL. They also consume very less amount of power. I'm talking about like 10 nanowatt, whereas TTL would consume about 10 milliwatt. So that's a huge difference. So in the small electronics like cell phones and tablets and other electronic gadgets, you'll see FETs being used, and they're actually working on increasing more density, meaning more gates in a small piece of area. So here were the rough comparison of the 2 technologies. CMOS, so we've been talking about having 2 levels, 0 and 1. So what is 0? Like if you have a voltage in a range from 0 to 5, what is considered 0 in that range of 0 to 5 volt, and what is considered high in a range of 0 to 5? And then these different technologies have their different ratings and standards. So in a CMOS technology, 0 volt to 1/3 of the VDD. VDD is just supply voltage, or VCC also you may see in some of the books. And the high voltage is considered 2/3 VDD to VDD. And in TTL, the low voltage is from 0 to 0.8 volt. This is how it is considered. And in high voltage is anything from 2 volts to VCC. And we'll see how different technologies, how the input-output voltage level changes. So this is a TTL technology. If you look at the voltage profile here, low is considered 0 to 0.8, which we mentioned also in the previous slide, and then anything from 2 to 5 or 5.5 is considered as high. The region that you see between 0.8 and 2 volts is referred to as an undefined region, which means if you have a signal that is creating a voltage between that range, digital system will not work because it doesn't know whether it's 0 or 1. Okay, so it's very important for us as a designer to understand what are those regions and how we can avoid them. For the output, if you look at the region for the low, it's very, very small, 0.4 volts. It's a very small range, and in any system, be it an analog or digital, we can have a noise. And what we know, a noise is an unwanted signal that could be induced into our circuit through the wires or any electrostatic charges on the PCB board. That may just induce some kind of noise or voltage. And if that noise or voltage is of this magnitude right here, it might just move our logic from low to an undefined region, causing a faulty behavior. So that's why it's very important to know these levels. Here's a good slide. I'm not going to go through all of it, but it just does a good job of showing what are the input and the output voltage levels for different kinds of technology. T-series, CMOS. This is one of the faster switching and accurate. So if you see, so what do you think if you have a very small region that defines low and high? Is that good, or if you have a high region that defines low or high? Which one is better? If you look at the bottom one, if you look at the high region for the input voltage, that's quite a big range, right? Is that good, or the one that you see, it's something like this over here, or something like this over here? Or maybe you can look at the inputs right here. Which would be better? Yes, Shri.
You'll have, if you use one of the ones with more of an undefined region, then if you get a higher or low value, then you'll be able to tell more specifically what part of the range it is. But there's a much higher chance that it will be undefined. Whereas if you have a smaller undefined region, then you will most likely get a higher or low value, but you won't be able to tell where it falls.
Correct. That is true. That is true. And it also depends upon the application as well. Okay. So for some applications, you want to go with the CMOS technology, which has a higher undefined region, because you're looking for more accuracy versus for this. So, but here's a good example of like what different kind of technologies have evolved over a period of time, or what are their threshold voltages. So something to look for. Low-level CMOS technology. If you look at this output right here, this is very, very, very narrow, very small, and a large undefined region. Whereas if you look at the input voltage, also reasonably narrow compared to the other technologies. The high is considered between 2 and 3, and low is considered between 0 and 1. Anything between 1 and 2 is undefined. Noise margin. Anybody know what noise margin could be? Any guesses? Okay, it's the tolerable difference between the input and the output ranges. Okay, that I'm talking about the difference right here from 2 to 1 volt. It's actually 0.8 to 2. That's the noise difference, because anything equal or above that can cause the logic to go from low to the undefined region, and similarly, can induce an error. If you look at the low level right here, the low noise margin is 0.2 volt to 0.8. So if you take a difference of that, it's around 0.6 volt. So imagine if you are at 0.2 and the outside error or noise is 0.6, it's going to push you from 0.2 to say you are at 0.2 volt, the noise is 0.6 volt, it's going to push you from 0.2 to 0.8 volt, very close to the region which is the the undefined region, right? So you have to make use of those things. Okay, this is also a very important characteristic of any IC. Propagation delay. Anybody know what propagation delay is? Anybody want to guess? It is the speedness or the quickness of the response to the change at the input levels. Okay, say you get logic A. This is the inverter. The input is defined as A, and you get the output. If A is 0, what is going to be the output? It's going to be 1, right? When I change the A to 1, the output is supposed to go from 1 to 0. The amount of time it would take to switch from 1 to 0, that is what we know as a propagation delay. And unfortunately, even though we have reached quite a bit of quickness and speedness in terms of the delay, but there is a tiny amount of delay which is considered huge in digital electronics. So if you look at the ASTTL technology, their delay is about like 1 to 2 nanoseconds. CMOS around 2, TTL 2.5, 3 nanoseconds. The earlier one that came out, 4000 series, and the standard TTL, those had higher delays ranging from 10 to 40 nanoseconds. So here's a good timing waveform that describes the delay. So say you input, initially it was 0, and then after reaching a certain time it goes from 0 to 1. And see, it's sort of like a linear. It changes over a period of time. It doesn't go straight to the 1 right away. It takes a little bit of time to go to 1. And then again, when it goes from 1 to 0, it takes a little bit of time to make that transition. And therefore, you also see a delay here. The change doesn't happen right away, but it takes a little bit of time and then goes to 0. Okay? So this region right here, when the input changes and the output reacts to that, that delay is known as the propagation delay from low to high, which was 12 nanoseconds for this inverter. And similarly, the TPHL is the propagation delay going from high to low, which was 7 nanoseconds. And it is okay that they can be different. These two delays can be different. In some ICs, they may be same, but in some ICs, they may be a little different. Okay. Now, most of the stuff from now on, it's pretty basic, and I'm just going to run through it because I got a lot of slides and I just want to finish it. This is probably our last lecture where we are doing this, PowerPoints. After this, whatever we have done like in the previous lectures. Okay. So, NOT gate, we know input is 0, output is 1. How would you represent a NOT gate in Verilog? Also, guys, remember, I've been trying to make videos for you guys. And then you see those videos and then you come to lab, so that should help you. It's not a Verilog heavy based course. I'm referring to the class, okay? You are sort of like independent on learning how Verilog things work, okay? But I had been trying to incorporate as much with the given time I have to help you learn Verilog, but I really want you to work on it independently, okay? Because lab will require you. All right, so how would you represent a NOT gate in Verilog? Using this sign, tilde, and then X. So say you are making a machine which does the invert of whatever the logic is at the input. So you start off with saying module space, the module name, which I define it as NOT underscore gate. Make sure Verilog is a case sensitive language and you don't want to have any spaces in there. It is okay to use hyphen or underscores, but make sure you don't have any space between the name. And in the parentheses, you define your inputs and outputs. So the topology is very much similar to other programming languages. Input X, output Y. And then semicolon, that means you're moving to the next line. Assign is a command that we use in order to perform an operation, and we are performing operation on Y. Y equals apostrophe X, which means it will take an invert of it, and then you end the module. That's a very basic 3-line code. Verilog is very easy to understand also because it's a textual representation of your logic diagram. All right. NOT gate, Verilog is a hardware descriptive language, and there are some other as well. And this is how it will be represented in different languages. In Verilog, it can also be represented as NOT, and in parentheses output, comma input. So there are multiple ways of doing it. I thought the other one was the easiest one. If you have a NOT gate connected to another NOT gate, it will basically give you whatever you had at the input, right? And here's a truth table of it. So if 0, x was 0, goes through an inverter, goes to 1, and it goes to another inverter, goes to 0. So this is basically equal to x right here. Okay, we refer this as a truth table. Here's an example of the NOT gate. So here's a temperature sensor. If the temperature is above 20 degrees centigrade, then the central heating is switched off. Okay, all right. Temperature above 20 degrees centigrade, that means it's going to create a logic of 1, right? 1 goes through an inverter, you get 0 at the output. 0 would mean off, so central heating will be off. Okay, it's a very, very simple application of the NOT gate. Moving on to the AND gate. Again, you got two inputs, wires X and Y, and the output is Z. For the AND gate, we know the logic, the way it works, when both the inputs are high, the output is going to be high. So when both inputs are high, output is high. Rest of the other combinations, it is 0. How would you represent that in a Verilog? You use that AND operator between the inputs. Say if you have another wire here, another input, X, Y, and Z, then X, Y, and let's say A. So then it would be X ending with Y, ending with A. Okay. Boolean expression, we'll talk more about it, I think tomorrow. Boolean expression is just a way of simplifying the expression for a logic diagram. So how the Verilog code will look like for an AND gate. Again, module space, name of the module, AND gate, you define your inputs X, Y, and Z. You can further say this is input X and Y. So X and Y are the inputs and the output is Z, semicolon, and then assign Z equals to X ending with Y, and then you end the module. So it's the code is very simple right here and easy to understand. Here are different hardware descriptive languages and how would you represent AND gate. We will be using this right here. Okay, here's an application for an AND gate. It's a burglar alarm. So if both the person sensor and the alarm switch is going to be on and off. It's user dependent. So user can either set it to on and off. So maybe when you are going to sleep, you want to leave it on. And if both the person sensor and the alarm switch are on, then the burglar alarm is activated. So this could go maybe on the door handle of your door or your car door on the inside. Alarm switch is always on. Whenever someone tries to sneak in, the sensor goes 1. When both the inputs are 1, it's going to generate an alarm, right? So moving on to OR gate, the logic of the OR gate says when any of the input is high, the output is high. When both the inputs were 0, the output was 0. How would you put it in a Verilog? You use this vertical line between the variables. How the Boolean expression looks like, it's pretty much X plus Y. It's a mathematical expression. How would you do the coding for the OR gate? You define your variables here, X, Y, and Z. Input X, Y, comma Y, output Z, assign Z equals X, this vertical line Y, and then ending it. So pretty simple. These are the different representations in different languages. The application of an OR gate. So it's a doorbell. You got one at the front and one at the back. If either the front doorbell switch or the back doorbell switch is pressed, then the doorbell rings. And we saw one application earlier for an AND gate and an OR gate for that light bulb also. This is what we refer as a timing waveform. and we will be doing a lot of it. So you got x and y. On the x-axis, you got this time, which could be in nanoseconds or milliseconds. So when x is 0, y is 0. For AND gate, it's going to create 0 because both inputs are low. For OR gate, it's going to be 0 as well. For NOT gate, which is invert of x, so x is 0, so x bar is going to be 1. And similarly, if you look at this array, when x and y both are set to 1, the AND gate is going to produce a logic which is going to be 1. OR gate is also going to be 1. And not invert of x, because x was 1, so invert of x would be 0. Okay, so we'll be doing a lot of that. Basic logic gates, bubble to bubble logic. Does anybody know that? Has anybody heard of that, bubble to bubble logic? It's actually a shorthand of invert gate. There is a way for us to convert the AND to OR gate or OR to AND gate by using these bubbles. Okay, say you are working, you're a designer and you're trying to design a circuit and you ran out of OR gates. You can use AND gate to create OR gates. And how? You can use these bubbles. Okay, so bubble on the input or output of a logic gate means to invert that input or output. It is a shorthand for NOT. Bubble pushing is a technique to apply De Morgan's theorem. This we will do tomorrow to the logic diagram. Change the logic gate AND to OR and OR to AND. Add bubbles to the, how we do that? We add bubbles to the inputs and outputs where there are none and remove the original bubbles. Okay, we'll do see one example right here. So say you had an AND gate and you want to convert that AND gate into an OR gate. You just add bubbles to the inputs and outputs. Okay, these bubbles, they represent inverter. Okay, do you see any disadvantage of doing that? Yes.
It adds clock to the circuit.
Yeah. Maybe it might work for someone who is trying to make for some application where the delay is not really important, or the size or the performance or efficiency is not really important. He's just looking for some LED which turns on and off for some reason. But notice when you are you're adding complexity to your circuit. You're adding 3 inverters, meaning you need 3 inverters. So you would need 3 wires to connect the input of those inverters and those outputs. So more wires, more delay, more bigger circuit, and then the delay between them also. So you're adding a little bit of complexity here. But sometimes we have to do it. We don't have any other option. How would you convert an OR gate to an AND gate? Again, you add bubbles to the input and the output. Here you have an OR gate. A is actually bubbled. Okay, so this is going to be removed. You add bubble here, you add bubble here, and you change the OR gate to AND gate. Okay. Similarly, over here you have an OR gate. The output is bubbled, and one of the input is bubbled. So you remove all the bubbles, change the OR gate to AND gate, and you add bubble where there were none. Okay. NAND gates and NOR gates. These are very important gates, NAND gates and NOR gates. And they are also referred as universal gates. All the chips, most chips that are used for faster applications and because they have smaller size and faster speed, one of the reasons is because they utilize NAND gates. NAND gates are a lot more cheaper. Their delay is down to few nanoseconds. And if you make a device with AND gate and OR gate, and if you make the same device with NAND gates, it's going to be almost 700 times more cheaper. So most people actually use NAND gates to make devices because they are very, very cheaper. And they can, similarly, just like you can convert OR gate into AND gate, you can make any gate with NAND gate. You can make OR gate with NAND gate, AND gate, inverter, and I'll show you one slide. So this is referred as a universal gate, and it's mainly because of the economic aspect of it. So how the NAND gate would look like, you get X and Y inputs, so Z is the output. And if you notice, it's basically an AND gate with a bubble. right? So it is going to do the invert of AND gate, right? So if you remember, the logic for the AND gate was when both the inputs are high, output is high. But because NAND gate is an opposite of AND gate, so this is 0, and all of the rest of the combinations you get 1. How would you put it in a Verilog? Well, you use this AND operator y, and then because it's an opposite of AND gate, so you use this tilde thing. Boolean expression x dot y. This is how you represent AND gate, and because it's an opposite of AND gate, so you have this bar on the whole thing. You see, if you see this x dot bar, or if you see that complement sign, those are same things. So don't get confused between the two. Here's a NAND gate again. And if you want to convert this NAND gate using the bubble logic to OR gate, you basically add bubbles to x and y, and then you remove the bubble over here. Okay. And here what they did is they basically tried different combination for x and y, and just to prove that z was same in both the cases. And if you look at z, it was 1110 here, and also z 1110. So this just proves that this logic circuit is equivalent to this circuit right here. Okay. Another representation of a NAND gate could be AND gate and then adding an inverter right next to it. Here's the application for a NAND gate. It's a device failure alarm system. So when all the three, say you are working in some facility and they want to keep a certain temperature, so they have these fans working, and you want to make sure all the fans are working, because if any of the fans stop working, the temperature goes up and it just may create an alarm. Or so this is what that system is. When all the fans are working, the input to the NAND gate is 1111, and the output is 0. If any of the fans stops working, the output of the NAND gate becomes 1 at the output, which activates the alarm. Okay. This is the NAND gate as a universal gate. Okay, so how would you make a NAND gate a NOT gate? How would you create a NAND gate to AND gate? How would you create a NAND gate to OR gate? This is how it is. So you basically have to, if you want to convert a NAND gate to OR gate, you take a NAND gate and you take another NAND gate. So you take two NAND gates, and the output of these two NAND gates goes into another NAND gate. Okay, but because the size is so smaller, even though we are adding more wires and more gates, whereas we could have just used one OR, it is a lot more. This is a lot more cheaper to make versus making a device with using one OR gate. So that's why a lot of people, they prefer NAND gate, and the size of the NAND gate is also smaller than that of the OR gate. So that's why it's considered as a universal gate. NOR gate, again, also a universal gate. When both the inputs are high, the output, when both the inputs are low, the output is going to be high. For the rest of the other combinations, the output is going to be 0. And again, if you look at it closely, it's basically OR gate with the bubble at the output. So it's an opposite of OR gate. The expression in a Verilog would be X, and then you use this vertical line Y that you use for the OR, and then this tilde sign, basically the opposite of OR gate. The Boolean expression for X, Y for an OR gate is X plus Y, and you've got a bar on the whole thing because it's an opposite of OR. So this this horizontal line represents a complement. Again, another representation for a NOR gate could be this OR gate connected with an inverter at the output. And here is an application for a NOR gate. So you have a power converter which is connected to the motor, which is basically mixing all the ingredients in the tank. So it's a stirrer, and you got 3 ingredients, say A, B, and C, and you got a sensor right there at the bottom of those cylinders. When all those ingredients are full, the level is above the sensor, they're going to create a logic of 0, 0, and 0, which means the output you get 1 and the power is power is being supplied to the motor and it's stirring the ingredients. When the ingredients go below the sensor, one of the logic will go to 1. That means the output is going to be 0 and the motor is going to stop. Okay, and it will create an alarm so that tank could be filled in with the ingredient and the process will start again. So here's an example of the NOR gate. Cool. I got 2 more slides. Okay. All right. Just like I had one slide for NAND gate, which was telling you how to convert one gate from the another. Here's for the NOR gate. If you want to make an inverter out of NOR gate, you basically take that input and feed it into the NOR gate. If you want to convert a NOR gate into AND gate, how would you do it? You take 2 NOR gates, and the output of those 2 NOR gates goes into another NOR gate. So in homework or in the exam, I might ask you, hey, we have a circuit which contains inverter and AND gate. We don't have it, but we still want to fabricate a device using NAND gates or NOR gates. How would you do it, right? So wherever you would have AND gates in your circuit, you will replace that with this whole thing right here. Okay, make sense? We'll do many examples of this. Don't worry about that. Here's one logical example with some kind of rationale. Here's some guy who works in an office. He has this parking area, say in a basement, and he works at some floor. So he takes the elevator from the basement garage and then goes up. We're trying to find out whether that person needs to take umbrella with him or not. And he probably brings his own lunch. So once he is in his office, he never leaves. He just goes to his house. So raining, or there's a forecast rain going into the ore. Driving car goes through an inverter. So say it's raining, which is going to create what logic? 1, right? 1. Now regardless of rain, obviously it's raining, so rain, there's a forecast. So 1, 1 go through ore, you get what here? You get 1 here, right? Okay, all right, let's move down here. Say he is driving his car, which means what here? 0, right? So you get 0 here and you get 1 here. That means he doesn't need to take umbrella, right? Say he is not driving, okay, and there's a rain forecast. So what would be the logic levels here and here? 1 and 1, that would mean he needs to take umbrella, okay? So this is like a textual, I put it this way so we can understand how our computers that we would make using these logic gates are able to make decisions for us. But I'll see you guys tomorrow, and we'll do some more of these examples. Okay? Enjoy your rest of the day.